We are going to have a short talk regarding programming competitions and approaches, solutions for some kind of problems you might wish to learn more about. However, one of the most important things is psychology when you compete in a real-time competition. When you're at home, it's pretty easy to drink some tea, to spend some more time, to relax and to solve the problem. But when you have this time pressure, it might be much more difficult for you to handle everything and to act as you would at your home. So that's why you have to learn how to feel comfortable, disregarding the other people competing, the time that is pressing on you. So first of all, we will start with a short presentation of everyone who is present at the lecture. So I will start. So what I want you to do is to say a few things. First one, just introduce yourself. Second one, mention the best achievement in programming competitions you have, or the achievement you are most proud of. The second one, your goal in programming competitions. For example, you want to be a world champion, or you want to be the champion of some part of Bulgaria or something like that. And the third one, your suggestions for CodeIT competition. How to make it better or different, or what would you like to see during the next editions. So I will start. So let me write it down. So the first is introduction. Second one, best achievement. Third one, goal. And the fourth, suggestions for CodeIT. Okay, so my name is Vasyl Biletskyy, and I am from Lviv, Ukraine. I work at the university as an associate professor, and the achievement I am most proud of in terms of the programming competitions is a gold medal at ICPC World Finals 2008 in Banff, Canada. My goal in programming competitions is, of course, to win a CodeIT in the future editions. So in my suggestions for CodeIT is the first, to have 2 separate tracks for marathon and for sprint at the finals. So whenever you advance to the finals, I suggest to the organizers to have 2 different competitions on 2 different days. The first one like we had yesterday, and the other one, for example, it might be today, the sprint competition. It might attract more competitors from different parts of Bulgaria or even some foreign countries. Sure.
You said it would be difficult to be implemented because American competition should consist of several days, please.
Yes.
Not 5 hours. For example, the task we were given yesterday was quite difficult for 5 hours.
Yes. Yes, but what I am saying, we can keep the track we have already, and besides, we can have a different track on the different day with a bunch of algorithmic problems, and have just a regular ACPC contest for individual contestants. Okay, so that's it. Now, just come up to the stage and give a short speech, but we don't have much time, so please.
First, some quick introduction, okay? My name is Vasyl. I'm from Prague. It's in Bulgaria. Well, that's the introduction. My best achievement, I'm not exactly sure. I would say it's from the junior button you get in informatics. It's a silver medal. And about the goal, I think it's, for now my goal is going to IY, but I'm not sure if it will happen or not. And the suggestion about CodeIT is, well, something like your, but I just hate marathons because they don't have a solution, and it's, in my opinion, the sprint type of competitions is really better. And either it's better having two separate tracks or just having one track. And it depends on how people want it. Like there may be a vote who wants a marathon competition and who wants a sprint competition. And if there are more people who want a sprint competition, they should do a sprint competition. And if there are more people who want a marathon competition, there should be a marathon competition. So, yes.
Okay, thank you. So regarding the goal, I'm not sure if my goal is going to be true in the future. I'm really not sure. And I have another suggestion for the future CodeIT contests. I really advise organizers to have only Bulgarian food during all the events. Okay, so go ahead. Yes, go ahead. You have to fight your stress. If you want to, you can speak Bulgarian or Ukrainian.
Okay, my name is Peter. I don't know if it's my best achievement, but the one I'm most proud of is the gold medal I won this autumn in an international contest that Bulgaria organizes every year in Shumen. And I don't want to share my goals because this makes me more likely not to achieve it.
So
But I want to perform better in contests. And my suggestion is also to make a sprint contest on finals and pay more attention on the correctness of the test data on sprints.
Thank you.
My name is Ivan. My best achievement is probably a silver medal at the junior program in informatics. My goals is probably advancing to IOI or ACM. ISPC. My suggestions are just completely remove the marathon and the finals and replace it with the sprint.
Okay.
My goals are, because I already graduated school, maybe the university students competitions to be good, to have nice results at them. And for suggestions, I'm not sure. Really not sure.
You are happy with the same thing. Okay, thank you. Okay, go ahead.
I am Todor. My best achievement is the second place I took last year on CodeIT. My goal is to qualify for the final round of Google Code Jam. And for the suggestion for CodeIT, it would be really nice if the site is open for practice and you can practice past problems after the competition or some problems from previous contests.
So do you mean regular Google Code Jam or distributed?
Regular and yeah.
My name is
Vasyl.
I'm from Kosovo. My best achievement is silver medal at the international tournament in Shumen. My goal is to win more medals in competitions, and in my opinion, CodeIT should keep the marathons since it brings the uniqueness to the competition. In my
Yes. Thank you. Go ahead.
My name is Brit. My best achievement this year I ranked first in marathons in the competition. I don't be probably qualified for the ICPC finals since I'm going to be university student next year. And since I want to throw Ivan, my suggestion for CodeIT is to remove all the springs and leave only the narratives.
Oh, okay, very nice.
My name is Daniel, I'm from Yambo, and I think that my biggest achievement is that I won a silver medal last year from international competition in Belgrade, Serbia. My goal is to go to ILI, and my suggestion is the same as your first suggestion. They should make a marathon round to the final, but also sprint.
Yes. Thanks.
May I ask something?
Sure.
If we make two separate competitions in the finals,
Yes.
who is going to compete in the sprints and who in the marathon?
All of you. If you advance to the finals, my suggestion is to have two separate tracks, and all the contestants, they have to compete in both marathon and sprint. And that would be pretty unique because there are no other competitions like this. And also, since these elimination rounds, they include sprints and marathons, so that would be a good idea to have two separate tracks on the finals. So please.
Hi, my name is Dubrin. I'm from Gabrovo. My best achievement is a gold medal from autumn informatics tournament, and my goals are to go to Junior Balkan Olympics in informatics, and my suggestions for CodeIT are to add second day in the final round.
Yes. Thank you.
Hi, I'm Victor. I'm from Sofia. My best achievement is a gold medal in the National Olympiad Informatics. Okay. My goal is to go to IOI, and I don't have any suggestions for going. I'm happy.
Hello, my name is Christian. I'm a high school student and I'm from Varna. My best achievement probably is a gold medal from the unofficial Balkan Junior Olympiad in Informatics. My goal probably is to go to IY and get a medal. For CodeIT, I have a suggestion similar to what you said, to have two separate tracks, but throughout the whole year.
Okay.
And for example, the top 10 students from the sprint track and the top 10 from the marathon track get to the finals, and they get to do both a marathon and a sprint competition here.
Yes, yes.
In two separate days.
Thank you. Thank you. So guys, please come up to the stage. So let's make it harder now. Let's make it harder. Let's add another one. And that's a fun story. Okay, so now you have to tell us a fun story. No, it's not optional. It's mandatory. So it's your turn actually right now. Yes, so go ahead. Do you have some fun stories in mind?
Well, actually, I need to think about talking about the other things.
Just any of them.
So I'm Andrei from Sprague-Grundy, now from Sofia. My best achievement is silhouette boy, not much, but still. Well, my goal is to do well at least at the university contests and do well at work too. My suggestions for Code, that's really interesting. Well, actually,
Since you are one of the organizers,
yeah, I actually do have suggestions, but since I'm an inside personality to them, like they're just ideas that I come up with.
just go
I
ahead.
have no idea to implement them. Well, something I thought of recently was that the scoring, which is for example, like it was this final round, your score plus 1 divided by the max score plus 1, that on the second power. It kind of brought some problems because of anxious results. So maybe we can think of a more flexible formula that works on all contests, and we don't even have to set the formula. But we'll think about that because it may not be possible. And yeah, there are other suggestions for me too, but there are too many to list. And we're almost already working on them anyway. Which reminds me, we're also going to work on the practice tour probably this summer. So we should be able to do that later. Fun story?
So the fun story. I believe that your fun story is the story about the visualizer.
No, it's a depressing story.
It's depressing for you, but it's funny for us.
Okay, so before the final round, I stood up till 4 or 5 a.m. to really polish that visualizer, to make it flawless with no bugs and to make it look pretty good. But I overslept because of that, and I couldn't still comment and echo that it was fine. So yeah, they didn't show it to you in the contest, so it was kind of useless. But you can see it after the lecture if I go to work and put it there.
Yeah, just let us know when it's available.
Yeah, and something even more depressing. What was it? Okay, so I have an exam after 40 minutes. But even the ones who are going to, like our teachers, you can call them that, they don't know in which room it will be, and if it will be our group or another group from our class. So yeah, it's really just bothering me.
Okay.
But it's also funny in
Thank you.
in a subway.
Go ahead.
My name is Maria. I'm from Sweden. My best achievement is gold medal on international tournament.
International tournament?
Yes.
My goal is to have a medal from IY.
Very good.
My suggestions for CodeIT are to give sprint and marathon.
Very good. Do you have any fun story in your mind? Maybe in Bulgarian?
No.
No. Okay. Thank you.
I may add something. You should change your dot orange English button, maybe.
Or you can have many goals. Okay, thank you. Go ahead.
They should know.
So I'm coming from some from competitions, some other one know from yesterday, and I'm part of CodeIT from this year. My best achievement is maybe 5th place on the national competition in Bulgaria and about 120 place on CodeIT Forces Division 2. my goals was to qualify for IOI, but I couldn't finish while I was student. And now my goals are maybe to qualify for the ICM next round, not only the regionals. Suggestions for CodeIT, I have many, but I'm working for them, of course. And fun story, at the moment I can't remember.
Come on, nobody tells us a fun story.
Okay, we are waiting for the fun story.
Maybe if I remember one about the CodeIT season, I will tell you in the lecture.
My name is Simeon. I'm 18 years old. I'm from Yabo. I'm programming since I was 6th grade. My best achievements were a few years ago when I won a few medals. My goals, I'm not sure what are they now, but I guess I want to go on IOI next year, which is my last year. So please let me go on IOI.
Okay.
My suggestions for CodeIT, I really liked your idea about the sprint competition in the finals, and I think that they should sum up the points from the marathon and the sprint, maybe.
Yes.
And it will be more interesting and more challenging because there will be two types of problems, and you will have to show your creativity. Fun story. I can't think of anything. Sorry.
No fun stories in Bulgaria. Come on.
We turn out to be very boring people.
Hello, my name is Ian and I am from Schumann. I don't have very good achievements in informatics, but my goals are connected with the university. I just got graduated from high school, and I want to start working in Musala maybe, and maybe CodeIT. My suggestions are, I support your idea for the second day, and that's all. Thank you.
Thank you.
Am I the last one?
It seems so.
Hello. As you should know, must know, I'm Vasyl from Schumann. My best achievement dates from 7 years ago. It's a bronze medal in Junior Balkan Olympiad Informatics. But recently, my best achievement is making you happy, all of you, in the last 2 days. Personally, it's better achievement for me. My goal is surely make it to the finals, ACM finals, ISPC. And suggestions for CodeIT. Believe me, I got a pretty big list, but it's not as easy as you think. Your idea is pretty good too, I suppose it.
Yes.
With 2 hands up. And I got a fun story. Yeah. It's it was programming training camp.
Yes.
Yes, for the national teams of Bulgaria. And in the last day, there is a team competition. We were grouped in teams, and whoever gets the first place gets the big cake or something, really nice prize. So the team who was second was one problem, has one problem less than the first. Yeah, it was something like that. And there were about 15 minutes to the end. And the two problems that made them first. The first one, they tried something really random, like print random mod 2.
Okay.
Yeah, it was kind of yes or no
Yes,
solution.
no.
Yeah. Weak tests, I guess.
Maybe 1 or 2 tests.
No, there were about 10.
Oh.
And they had about 2 solutions.
Yes.
Yes. And the second one was like scan number and print the same number.
Oh.
And it looked like a really high level mathematics problem, but in fact it was just
the given number.
Yeah. Yeah, so they got the first place and the cake. It was pretty funny.
Okay, thank you. Thank you. You have a suggestion? Any more suggestions? More fun stories? No? Okay. There is also a fun story from Ukraine. One of the contestants decided to get a job. So when he had to fill the form, the application form, there was a field children. Yes, and he wrote something like this. So they spent a lot of time thinking on what it actually means, like 6 boys and 9 girls, or maybe 6 adults, yes, out of 9 children overall. But eventually they learned that his wife is actually pregnant, 6 months pregnant. So that's why he decided to write 6/9. So, okay, so about the suggestions. So what we can suggest as the common opinion is to have 2 tracks. So the first one is marathon, and the second one is sprint. And like here you have a set of medals. Okay, medals. Here you have another set of medals, different ones. And in fact, you can have another set of medals which goes to the person who has the best result together. Yeah, so you just...
Or we can just
Well, in some way we have to combine the scores from both tracks, and we can have a third set of medals. So keeping the same elimination rounds and having 2 tracks at the finals, I believe might be a good idea for organizers to discuss for the future editions of CodeIT. Okay. Now, talking about your goals. If you do programming competitions, you need to have a goal. Otherwise, it makes no sense to practice or to prepare yourself. If you are just solving problems once a month, it might be a kind of a hobby. But if you want to improve yourself and if you want really prepare yourself for difficult and challenging problems, you need to have a goal. And you need to understand what you have to do in order to achieve this goal. The key observation is that everything is actually possible. You just have to train hard. Yesterday we talked about first solved problem. So some of you started solving problems at the age of 10, maybe even before 10. Some of you started at the university, but it's not late even then. I solved my first problem at the third year of my study at the university. Few years later, my team got a gold medal at ICPC, and we had a goal. We had this goal, but that was like the last goal. We started from something smaller, much smaller, like to advance to the second round of ICPC, yes. We trained, we read a lot about the algorithms. Eventually, we did advance to the next round. Then we decided to go to the regional contest, and we set up a goal to advance to the world finals. We did that, and then the final goal was to get a medal. We were lucky to get a gold, but if we got, let's say, bronze medal, we would be that much happy as we were in fact. So you have to understand that in order to achieve the goal, you have to work hard, and you have to learn from other people, and you are the one to motivate yourself in the first place. Someone might say that, well, in our school or our universities, there are no teachers, there are no professors or no coaches that would push us to train or to practice. But you are the first person to motivate yourself. When I started doing programming competition in my university, there were no one doing this among the students and professors. So we just started doing this. We started a school, and now in Lviv National University we have a programming competition algorithmic school which prepares students, high school students and university students for contests like IOI and ICPC. From 2008 until today, we got 1 silver medal at IOI, 1 bronze medal at IOI, and recently in Thailand we got bronze medal from ICPC. Well, along with the gold medal at 2008. So now we have a school. We just created the school. So you can do everything you want to do. If you are not happy with the coaches and subjects at your university, just suggest them to have different, like we are suggesting to CodeIT to have a different track. We can always do that. If we are not happy with this competition, just suggest something. So the same works for practicing and preparation for different contests. Nowadays, there are a lot of online judges, a lot of platforms like Topcoder, Codeforces, and other resources where you can test yourself, where you can try solving the problems. You can compete in online competitions. You can even advance to some on-site rounds like Google Code Jam. In fact, I did many of them, like Topcoder Open and Google Code Jam and Facebook Hacker Cup and many others. Also, you might wish to create problems. If you are not happy with the problems your university or your school has for your local competition, you can suggest the problems. You can be a problem setter, but that's a totally different story. So my message to you is, first, set the goal, and then work hard on yourself, and everything is possible. I believe more than 90% of your result depends on how hard you work on this. My students, before this ICPC finals, they had trainings 6 times a week. 6 times a week, except of Sunday. So every day they have 5-hour-long contest, followed by the analysis and upsolving. So they basically spend all the day. They go to work. They go to the trainings. So they spent a lot of time, and these bronze medals, that's not just a luck. That's a result of a hard work. So that's my message to you. Anyway, so our plan for today's lecture is the following. We are going to discuss something. Since these competitions, they are actually the games. These are like big games. So we will talk about the games. I received a lot of suggestions about what shall we discuss today. And since the time is very limited, I'll just pick some random topic and we'll discuss some specific games that are very popular among the algorithmic problems. At any point, don't hesitate to ask any questions you have regarding the game theory or regarding the general way how to prepare yourself for programming competitions. We are going to have a small break in maybe 30 minutes, and then we'll continue with game theory. Okay? Any questions so far? Great.
Just one question.
Yes?
Do you think that in 2008, your team would have been get the gold medal if they didn't have a good coach like you?
Could you please repeat?
In 2008,
Yes.
do you think that your team would have got the gold medal if they hadn't got a good coach like you?
If they didn't what?
If they didn't have a good coach like you? Because I think
In 2008, he was a competitor.
Yeah.
Well,
my fault.
in 2008, well, I started in 2005 or something like this. I solved my first problem around this time. And in 2008, I was like the first person in my university who actually started doing this. So I was a contestant and a coach at the same time. So I was the coach for other teams. So some contestants were older than me. So I was a pretty different type of a coach.
You said something like that if you don't have a good coach, it's not a problem, you can still be a good competitor.
Sure.
But I honestly don't agree with that.
Well, of course, if you have a good coach, you are in the better position than students that don't have coaches at all. But anyway, if you don't have a coach, it doesn't mean that you just have to give up.
Yes, of course.
You just have to spend more time. You need to give more effort in order to achieve a goal. Well, it seems that in Bulgaria you have a perspective. I mean, there are many teachers from schools that are interested in these programming competitions.
Honestly, the teachers that are really good and can prepare competitors for IOI finals are not that much.
Well, in Ukraine we have two, and Ukraine is much bigger than Bulgaria. Well, and also in terms of IOI results, you have much better results than Ukraine do. However, in terms of ICPC, we are doing much better than you do. The question is why? Yeah. Maybe you are not doing hard enough. And if a team of 3 students, if they set up a team, and if they set up a goal, they set a bar, and they decide to train and to prepare for the next regional contest, I believe it's possible. Given then you will have a lot of trainings and a lot of teamwork. For example, my team, we recently got this bronze medal, and now we have another team, and we already set up the plans for the next season. And we are looking forward to compete in the next final.
Most of the good Bulgarian competitors, they study abroad. So Bulgaria doesn't have. I don't think that Bulgaria has ever been to the finals.
Well, they actually went to the finals maybe 20 years ago. It was, yes. You do not remember those times.
Sorry for interrupting you, but that one of the brilliant competitors last year studies in Imperial College won qualified for the finals. And it was because of him.
Yes.
Gotcha.
So it's possible. It's possible, and if you set up a goal, it's not something you should be afraid of. Okay. Game theory. So whom of you are familiar with game theory, at least in some terms? Okay, great, great, very good, very good. So, as you probably know, there are many types of games which differ in several ways, like a number of players. There are games where are no players, which are called zero-player games. There are games with just a one player. Can you give me an example of a game with just one player? Well, it's hard to call them the games at all, but however, when you have a deck of cards and you have to put them in some way on the table, that's the game for one person. Two-person games, which are the most popular, and more than two-person games. For example, some strategic network games or some massive multiplayer games. Yes?
Also the version of chess which is with 3 players.
Yes, yes, that is also possible. So we will discuss two-player games today. From those two-player games, there are also many different types. Some games, they depend on some chances, on some probabilities. For example, if in the middle of the game you have to toss a coin or throw a die. For example, while playing backgammon, yes, you have the dice and you have to throw them, and your turn depends on some random choice. So we will skip this game for today. We will discuss the games where all the states are defined strictly. Also, the games might be divided in two groups. So the first group is called impartial games. And the second group is partisan. Every game can be described by some state. For example, if you are playing chess, the state is described by the set of chess pieces you have on the table and their positions, right? So you have game states. So let's call the set of game states with the letter S. And also, you have a set of possible moves, yes? Which is actually a function which takes some state and leads us to another state. So that's a move function. So for example, if you are in one of the states, let's say S1, so then if you take a move, then you will reach some state S2. However, you might have more than one choice at this point, right? So you can select where to go. So which means that you go from one game state to a set of the states, and you can choose which state you want to go to, which move are you going to make. So that's actually a set of states from S. So in case if this function is the same for both players, the game is called impartial, which literally means that both players are in the same position. So it doesn't matter whose turn is now. We have a same set of possible moves. If they have different possible move sets, then the game is called partisan game. An example of a partisan game is chess game, because you are playing white, I am playing black. So I cannot move your pieces. You cannot move mine. That's why we change the game state in different way. Yes. So we will start with impartial games. Okay. Also, some people call them symmetric games because move sets are symmetrical for both players. Okay. So we can think of the game states and those possible moves as a directed graphs. Let's imagine some graph. And these are possible transitions between the states. So some states are terminal or final. And for those states, we know what is the game outcome. Talking about the game outcome, we also can divide games into several different types. The first type is win or lose. So these are the games where one of the players is declared to be a winner and another one is declared to be a loser. Or it might be a case when the game is a draw. Another type of games is a zero-sum. Games. In these games, the outcome of the game can be expressed in terms of the profit the first player gains at the end of the game. For instance, how much money you will get at the end of the game. And if it's a zero-sum game, it means that your profit, your payoff is actually what the other player loses, or vice versa. If your profit is negative, it means that you actually lose this amount of money, and the other player, he actually gains this money. Okay, so, and of course, another type is non-zero sum games, which are also possible. So we will start with win or lose games. So in these games, one of the states is the state where we start from. And some other states are terminal, and for each terminal state, we know which player wins. So let's say if you get here, you will win. If you get here, you will lose. And if you get here, that will be a draw. When I say this is a winning state, I mean it's a winning state for a player who actually comes here, who makes the move which leads him or her to this state. So we just made up some game. Can you tell me, if you are a first player, do you have a winning strategy from the starting state?
You don't have?
Do we or we don't?
We don't have for the first player.
Yes, let's see. If we take this move, if we go here, then the second player will definitely go here and will win the game. So we will lose. If we go here, then there is just the only option for the second player, and he will lose, we will win. If we go here, then the second player will choose to go to the draw state. So this is the winning move for the first player. So what is the game strategy? The game strategy for a player is the set of rules which state where to go from each of those states, which is actually the function which takes all the states and moves us to some other state. What is the optimal strategy? The optimal strategy is the strategy which allows us to get as good result as possible, disregarding of the strategy of the other player. Well, literally, optimal means the best possible for all other strategies of the second player. So let's consider an example. Let's consider an example. So we have a number up to 100. We are giving this number. There are two players. Each player has to replace n with a number n minus d, where d is a divisor of n, any divisor, such as d is less than n. The player who cannot make a move loses. Okay? Let's see. Let's just play the game. So if n is equal to 1 and you are the player to move, do you have any possible moves? Any available moves? Yes?
Suppose that you're in a losing position.
Yes.
You're going to divide the number by 1. Never mind.
So if n is equal to 1, there are no possible moves.
It's a losing position.
Yes. So in game theory, there is a notion for such game states or game positions, if you wish. The position from where the next player wins, or the player to move, is called end position, or next player wins position. Positions where previous player wins is called P position, or previous player to win position. So here, if n is equal to 1, so is it N position or P position? It's a P position because previous player, yes, or another player who possibly made a move, he actually wins the game because we don't have any available moves. So that's a P position. So what if N equal to 2? Can we win this position? How?
If we get D equals 1?
Yes. So we can move here. Yes. So that's why it's next player wins position. How about N equal to 3? P, because we have only one choice. How about N equal to 4? Can we win from N equal to 4? Of course we can, because we can go to N equal to 3 or we can go to N equal to 2. However, it makes sense to move from N position to P position. Okay, and so on. Yes? Okay, let's just continue. For N equal to 5, 6, 7, 8, and 9. For N equal to 5, is it P or N? P. For N equal to 6, N. For 7.
If I'm not wrong, every even position is N position.
Not really. For N equal to 8, it's N, and for N equal to 9. Is it P? It's P. Okay. We cannot prove that. Okay. For N equal to 10, N, 11, P, 12, N, 13, P, 14, N, 15.
N equals 1 is a P position.
Yes.
For each other number,
Yes.
it can be divided by 1.
Yes.
So the previous position is either P or N.
Yes.
So they're going to swap each other.
Yes.
This is because the even positions are in positions.
Yes. Yes. Great. So we can actually, instead of 100, we can put whatever we want here. Yes. Let's change the rules. Let's change the rules a bit. Okay, so let's say that like this. What about this? If we cannot subtract 1, let's see what happens then. So that's P position, that's P position. That's P position. That's N position. P position. That's, what about 6? That's N.
Just all prime numbers will be P.
Yes, all primes are P. Okay, primes at 11 is P.
7 is also P. Oh, yes.
7 is P. So what about 8, 9, and 10?
Well, 8 is an N. It's an N.
Okay, yeah, that's true, because we can go to what? We can go to 4.
We can go from any composite number to any prime number.
Oh, really? Are you sure?
Well,
You're wrong.
So from 8 we can go to 6, or we can go to what? We can go to 4, or we can go to what? That's it.
Just these two.
That's these two. So n is 8 is actually p position.
No, to say that the divisor should be greater than 2.
Okay, I actually meant 1. Okay, so how about 9? 9 is a p position as well. How about 10? 10 is n position. So now it's like not that obvious if we can see any pattern in this p and n positions. However, there is a general approach how we can put this p and n marks to our game state. So if we have a graph, if we have a game graph, then let's first have no labels for all the positions, all the states, except of the terminal. For example, we have win, lose, or win. Yes? So then, for every position from which there exists a move to a p position. So that's something like this. So if you have a state which has a move or has an edge to a p position, then this state is definitely n position. Do you understand why? That's pretty easy. So that's why this is n. And this is n as well. And this is n as well. Yes? So and every game state that has all moves to the n position, like this one, all the moves go to n position, then this position is p position. So we can continue this approach while we can do that. And in this way, we will mark all the game position with either p or n. Yeah, that's pretty straightforward. I believe you understand this. So if the first thing we can do, if for a state S, we can assign a mark n to S if there exists such a state T So we assign mark n to the state S if there exists a move from S to some state T where T is a p position. And the second rule is then we assign a mark p to the S position if for all moves from S T is n position. It's pretty easy. So how to solve this problem then? With just a dynamic programming. And while implementing this dynamic programming, you are going to use these two rules. Can you write down a piece of code which actually solves this problem? Go ahead.
Well, it
So
should be a code or just a pseudo code?
as you wish.
Okay.
As you wish. So you are given a single integer.
Well, let me just write it all. It will be simple. Now in GPIC, I'll have an array which will be for the dynamic programming.
Okay. From this point, well, that's the good good chance for you to learn some game theory and a good chance for me to learn Bulgarian. So that's why you give all the commands in Bulgarian.
Добре, значи задачата ще бъде с замишлено оптимиране. Окей, в замишлено оптимиране ще пазим едно масивче. И това масивче за всяко n ще пазим дали е winning позиция, т.е. back, или дали ще бъде losing позиция, т.е. n. За сега всички го разбрат. Същата работа. Само n е до 100 или така ще е. Това ще бъде сложността, тя ще бъде n по корен на n.
Що корен?
Смисъл на администрация на n. Смисъл може по лог, обаче това е някакво да си го направи. Значи, ще напиша сега с n корен от n, защото това е малко по-лесно за писане.
Един съвет, първо пишеш алгоритъм, а после не определяш сложността.
Смисъл? Добре, окей. Сега, има едно задача. Почваме смисъл. Дайте първо да си направим всички прости числа, да са ни на лузинг позиция. Ще означим с 0. Хубаво, значи сега.
Just a small remark, since n is at most 100, you don't have to implement anything more complex than just two nested.
More complex, it's funnier.
It's funnier, but
okay, let's just write this.
As more lines you have in your code, as bigger the chance of some bugs in your code are.
Yes.
So if you can just put two nested loops, go ahead and do that.
D was from 2
Yes, from 2 to n minus 1. But it should divide n.
Well, this is the simple solution. And it's just simply we check every possibility, and if we have already, well, first of all, we for every e, which will be our number, and
are you sure that's Bulgarian?
Oh, I forgot. Значи, за първо пробваме всички и-та, след това пробваме всяка възможно d, гледаме дали и се дели на d и дали е било възможно и минус d, в смисъл, дали е лузинг позиция, и ако е лузинг позиция, следователно тук ще е позиция, сигурно сте win. И накрая, отговор в тъпа n.
Дали са тунели в началото, защото не се това.
Добре, не се. Казваме нещо отгоре, че имаме една горка, едно глобално. Това е някакъв мъсъл.
Добре, благодарим. Okay, so basically what we do here, we just apply this principle, these two rules. Yeah, so if there is at least one position, one P position, then this is N position. Otherwise, if all of them are N positions, then we just keep P position as we had at the very beginning. So this was pretty simple. Let's consider another more neat example of the game, which I gave as a problem for Ukrainian national ICPC contest in 2009. So the statement is pretty easy. So you have a card deck, but not all ranks are present. You have just 4 ranks: Jack, Queen, King, and Ace. And also you have 4 suits. So let's draw them. Okay. Okay. In Bulgarian, Jack is Valet. Dama. Pop. Asak. Great. Okay, then clubs.
That's spades, actually.
Oh, okay, sorry. Spades.
Clubs. Spatia.
Spatia. Okay. Diamonds. And hearts. Okay. So you have this 16 cards. Yes, you have 16 deck of 16 cards. 16 cards. 4 ranks, 4 suits. Okay. So there are 2 players. Each receives 8 card hand. So you have 8 cards. So the player with who has Jack So the player who has Jack of spades starts. When you make a move, so what he does, he just puts the card face up on the table. Every player...
The Jack of spades or any type of...
No, just exactly Jack of spades. So he puts the card face up on the table. And then while it's your turn to make a move, you have 2 options. First, you have to put a card with at least rank as the top card. Or you can take 3 cards from the table. If there are more than 3 cards. If there are less than 3 cards, you take all of them except of this Jack. He always stays on the table.
When does the game end?
So the player who manages to put all his cards on the table wins the game.
Then isn't it something like dynamic programming with big masks?
Maybe.
One big mask for the cards on the first layer.
Sorry? No, no. 3 top cards. Yes. So when you put a card on the table, yes, you put it on the top. And then if you decide to take 3 cards or like up to 3 cards, then you take them from the top of the stack of the cards you have there. So let's imagine you have Jack of diamonds then, and then Queen of hearts, and then Ace of hearts, and then it's your turn to move, and you don't have any aces. So you don't have a choice, you have to take these 3 cards. And if you decide, if there is no ace here, and you decide to take 3 cards, you cannot take 3 cards, you can take just 2. Okay?
Do you pick the last 3 or any 3 cards?
Top 3, yes, no, top 3. Top 3 cards, put a card atop a stack. Atop the stack.
State колко карти са видни.
So, now you have to switch to English.
So, okay.
Can I choose some sort of BFS or DFS?
Maybe some sort of BFS or DFS. Let's count the number of game states. That's very important when we are talking about the games. If you see that number of states is so huge that you cannot process all of them, then you have to figure out something more clever or efficient. But if you see that you have the number of states that you can actually fit into the memory, then it might be a good hint for you that you don't have to figure out something incredible. You can just use this principle that we discussed before, and you can find the P and N game positions. So what is the number of game states? Okay, how would you describe a game state?
Well, how many? Which card?
A bit mask for the 16 cards and account for how many cards did the one player.
Okay.
Yes, but how do you?
So we have 16 cards, okay? For each card, the card can be where?
Well, the problem is that you must somehow save the order of the cards that you have.
Can I take any 3 cards or just the last 3 cards?
Top 3 cards, last 3 cards. Last 3 cards.
Well, I think this is the problem with the solution with finalists. Because
and also that states are recycled.
yes.
So okay, anyway, we need an order. So let's just keep the order.
From lowest to highest rank. From lowest to highest rank.
Exactly. So it's easy to see that all cards on the table, they are actually sorted from the lowest rank to the highest rank. So you cannot put Jack atop a Queen.
Oh, is it then always optional to play your smallest card?
Sometimes you cannot play your smallest card.
Well, when the smallest card you can.
It's not necessarily. It's hard to say. Maybe it is, maybe it's not. Well, imagine that you have an ace and you can force your opponent to take 3 cards and then you just put the smaller card. So here we have ranks, but actually, are we using these suits anywhere? So does it matter if you have Queen of Diamond or Queen of Hearts? Does it matter actually?
Isn't one bigger than the other?
No, not at all. We are just talking about the ranks. Ranks.
Then it's not okay.
It's not what?
Then I don't think it's that hard.
Yes, it doesn't matter what is the suit of your card. It only matters who starts the game. So we have to check who has a jack of spades, and this is the player who starts the game. But besides, it doesn't matter what suits of the cards you have. It only matters what are the ranks of the cards.
Well, then we can save in our save where the last three cards. That's someone playing. But
so come on, guys. What is the state of the game? How can we describe the state of the game?
The number of jacks on the table, the number of queens on the table, the number of kings on the table, the number of aces on the table, and the big task of the one who has least amount of cards on his hand.
I'm kind of very sure.
Can you just...
Oh, no. And that. Well, yes.
Thanks.
So?
Well, like you said, the state is when you know what is the number of the jacks, queens, kings and aces on the table, then you can simply determine which are the last three cards.
Of course, but is this enough for the game state?
Well, you should also keep it bit massive.
Yes, and the
You should also keep the hand of the least amount of cards has in his hand.
The hand of one of the players.
Yes.
If you know how many, well, you want to know how many jacks are on the table, how many queens, and so on.
And now you need to know how many jacks and queens and so on are in the
one.
character of the one of the players.
Exactly.
Well, yes, that's...
And that determines the state.
Yes.
Same with the social activity.
Yes.
But we don't...
So for each rank, we need to know how many cards are on the table and how many cards are in the hand of the first player. Yes, the rest are in the hand of the second player. So, how many options are here?
2 to the 6.
Well,
really?
4 to the 4th.
4th power.
Okay, let's just consider one rank. What are the possible distributions?
4 on 4. 5.
Really? 5?
Well,
let's just write them down.
0, 1, 2, 3, 4.
Okay, so first player, second player, and rest is on the table. Yes. So 0, 0. Is it possible?
Yes.
Possible?
Yes. 0, 1, 0, 2.
Well, 25.
0, 3. 1, 0. 1, 2. 1, 3. Okay, there is also 0, 4. 2, 0, and so on.
Треба само подключити.
О, да.
Какво? Да.
Ще трябва да се подключи.
Трябва само подключити.
But there isn't just a big difference between 25 and 16, so...
Well, yeah. So how many these numbers do we have?
10.
We have like 5 plus 4 plus 4 plus 3 plus 2 plus 1. And it's equal to what?
15.
It's 15. 15. So we have 15 options, 15 possible distributions for one rank. How many ranks do we have? 4 ranks. So how many game states do we have?
5.4.
15 to the 4th power, which is approximately equal to what? To 16 to the 4th power. which is exactly equal to 2 to the power of 4 by 4, which is 2 to the power of 16. Can we afford storing 2 to the power of 16 states?
Yes. Yes.
Can we? Can we?
Yes.
Yes, we can. So let's do that. It's even less than 2 to the power of 16. So we have this number of states. And how about the set of possible moves? Can we generate all possible moves for the given state?
Well, yes, we have 16 possible moves on the first side. Well, less than 16, but let's say there are 16.
Yes.
16. Myślę, że może kliknę wся karta. Well, master player have yes.
So we have 15 to the power of 4 states, yes. And for each state, how many moves we might have at most?
In the worst case, 16.
5.
It doesn't matter what suit we use. It just matters what rank. So we can either put one card on the top. So 4
Okay, yes.
possible moves, or we can take 3 cards from the top. So for each state, at most 5 possible moves. So the overall number of moves is 5 by 15 to the 4th power, which is also affordable for us. Yes? So we have all the states and we have all the moves. So now our task is to decide which game states are P positions and which are N positions. How can you do that?
Well, we check if one player has zero cards, and if it's
Yes, but the same state may repeat multiple times.
yes, then we should add something else to the state, and this is which is the current player.
The game
Something
graph
like
is that, and then
So, well, these states and these moves, they form a game graph, yes, a directed game graph. So we know that some states are terminal when one of 2 players has no more cards. This means that the state is terminal. Yeah, and for other states, we have to use these 2 rules. How to decide on whether P or N positions we have.
May I ask something?
Yes.
Are you sure that the game is acyclic?
In fact, it's not. It's not. That's the issue of this game, because the previous game, it was they call this kind of games acyclic games. They call them recursively bounded, which means that it doesn't matter what strategies are used by players, the game eventually ends, yes, no matter what they do. In this game, it's not true. We can play it forever. So that's why this game graph might, and actually it contains cycles. So that's the issue, that's the problem of this game. So how should we handle it?
Can we compress every strongly connected component into a single
That's an
process?
overkill. Future.
Cool.
Well,
Can we
that
change
is
the state so that it becomes acyclic?
How?
Rozładowałem rozstawę, coisa que custa criar. E só foram já que nos next
So we cannot use some recursion, like memoization or direct dynamic programming. We cannot use because of these cycles.
Well, can't we just make 3 types of answer? One is a draw, one is a win, and one is a lose. And every time when we move through any state, before we recursively call all other states, we just pick the current states to be a draw. And always, for every state, if there is a possible draw, we draw. If there isn't a draw, we just make it a win.
So, was almost like this. So remember, we have two rules. First one, we can assign a mark P to some state when what? When all edges from this state leads us to end state. And the second rule is we can assign n to the state when there is at least one move which leads us to a p state. So all we have to do is to apply these two rules. But we will not do this from the beginning of the game to the end of the game. We will do this from the end of the game back to the beginning of the game. How? We know terminal states. We know terminal states. So every time we get some new information out of these rules, we can go up and up and up and check if we can gain more information. Using just these two rules, when we're done, when we can get no more marks, it's over. And all the states that have no marks, they are the states for the draw, which in fact for this game, for this particular game, means that for those states, players will play forever. They will never stop. I can show you a very simple example. Okay, over here. If we have something like this. So that's it. That's it. That's the terminal, and that's P. So if it's P, then this one is N, right? So, and what is this state? Let's say we start from this point. So the first player takes us here. So the second player has two options. He can either go to the end state, but it makes no sense to go to the end state. Or he can go here. If he goes here, then the first player will go here and the second will go here, and the first player will have the same choice. So they will just stay in this cycle forever, because it makes no sense to go out of the state. So here we have P, we have N here, and we don't have any marks for the cycle. And that's the example of the game where it can last forever.
But in the cycle, it's an even number of nodes?
Yeah, for the odd number of nodes. If we have even number of nodes, it still makes no sense to go out of the cycle.
In the next cycle, then the other player will be in the position where he should choose to make another cycle or go to the winning position.
Yes.
So I don't think it's easy. If it has even number of nodes, it will be a draw.
Well, you mean even number of nodes in the cycle, or in the cycle? So let's add another. If we add another, that's still a cycle, and we won't get out of the cycle ever.
Could you repeat once again?
If we have 4 vertices in the cycle, every time a player gets here, it makes no sense to break the cycle, to go out of the cycle. He will continue this way, and this will last forever. So that's the small example. And in our game, we will have the same stuff. For some game states, players, they will just make moves infinitely many times, and it will never end. And we will declare this as a draw. Yes. So, who would like to write down a piece of code?
No thanks. Little bit huge.
Well, not necessarily all of it. Maybe some pseudocode. Well, actually. So anyone? Anyone? No? Okay, so.
Just a quick question about the cycle thing.
Yes.
Why would it be always optimal to continue doing the cycle if we can win from, for example, if we can win from this one, no?
How?
Well, if this was a P, and then the whole cycle.
If it's a P, it's. Yes. So let's imagine if it's a P, like this, that's P. Then it's definitely that's N. And if it's N, then what? Then that's P. Yes. And that's N, and that's P, and that's it. So we have a cycle, but however, we can mark all the vertices. So it's not necessarily if some state is in a cycle. Yeah. So you just really have to run this loop. So I will write down the pseudocode. Okay. So we will have. So while we have any changes, yes, we say that change is false. Then for each game state S with no label, we repeat. We just check two rules. Simply check two rules. If there is an edge ST where T is P, losing state. Then what? Yes, then put the label N to our state and let's say that change is true. And also if all edges ST are such that T is N, then we do the same. We say that S is now P and change is true. So that's the pseudocode. You cannot implement just this because you will get a time limit, of course. You have to work on some technical things, and you have just to keep some queue of states that are potential that might be candidates for these checks. And since you have only 5 times the number of states edges, you can add every time you get some new information, you can add all the neighbors for this state to the queue of the possible candidates. And this will still work and fit in the time limit.
Why do not draw position?
What?
Why do not draw position?
So when you finish this, those states with no labels, they are draw positions, or positions where players continue playing forever.
This does the same thing as the one I said, but it's just iteration.
Yes. Any questions?
Can we do the same thing with compressing chemistry and connecting into a single vertex?
Well, in fact, you can.
Okay.
Yes, this is
Okay, so let's have a 5 minutes break. So, another very important part of the game theory is it's called pile games. Ah. So, and who knows Nim game? Raise your hand, please. So. Game of Nim. Okay, so let's see how to play the Nim game. We have a pile of n whatever stones, and in one move you can take at least one, at most all stones from a pile. So let's consider one pile game, one pile Nim game. So you have n stones. So the player who cannot make a move loses the game. That's the normal game rule. So if you have one pile and there are n stones, what is the winning strategy? What? Take all the stones. So if we have two piles, n and m, do you know the Nim game? Do you know Nim game?
No.
No, you don't. So imagine you have two piles with m and n stones. And in one turn, you can take as many stones as you want from one of the piles, but at least one. The player who cannot make a move loses. What is the winning strategy for two pile Nim game?
Take n minus 1 or n minus 1.
No. Take from the one. No. Take from the pile which has more stones.
Make them even and then copy.
No, make them equal.
Make them equal.
Must be just yes.
Yeah, so P position here is NN when there are the same number of stones in both piles. So if you have the same number of stones in both piles, you cannot win. If they are different, you just make them even. That's it. Okay, so and if you have three piles, what is the P position for three piles? Who knows? What is the P position? So ABC is a P position when A plus B plus C is equal to 0, where plus is exclusive bitwise OR. So in C++ programming language, there is a XOR operator. In Pascal, you have XOR operator. So it is a bitwise operation, which is exclusive disjunction. 0 plus 0 is 0, 1 plus 1 is 0, and 0 plus 1 or 1 plus 0 is 1. Yes? So you know this. For those who are not familiar with Nim game, just Google it and read about the Nim game. It is like very, very popular. Okay, so you know how to play Nim game. Let's consider an example. If you have 1, 8 and what else? 7. What is the winning move in this from this position?
Always bring the opposite player to the position.
So 1 plus 7 plus 8 is equal to what? It's 14. So we want to make it 0. How can we do this? If we write 6 instead of 8, we will have 1 plus 6 plus 7, which is 0. Yes? It's pretty easy. So, like I said, the player who made the last move is a winner. This is a normal game rule. On the other hand, there is a Miser rule, game rule. Okay, so we have normal game rule, and there is also Miser, from French word Miser, game rule, which states the player who made the last move actually loses the game. Can you solve Nim game? Can you find the optimal strategy for Nim game in a case of Miser game rule?
No, well, want to be the same.
Almost the same.
But if the first player, if the XOR is 0, you just win, and if the XOR is not 0?
Not always. Imagine, so if you have 2 piles, 1, 1, can you win?
No.
Of course you can. Of course you can, but the sum is 0, actually.
Well, yes. What would be if the second player loses?
Okay, so it means that if you cannot make a move, then you are a winner. That's the Miser game rule. So it means that like all the terminal positions, they are now they are p positions. So all terminal positions, they are p positions for the normal rule, and for Miser rule, all terminal positions, they are n positions.
Well, we just subtract 1.
From what?
No.
It should be just the opposite. If you're in a winning position in your normal games, then it's a losing position and reserve games.
Well, not exactly. Okay.
Because when you're playing normal game, you know what move to make.
Let's play. Let's play the Miser Nim game. So I pick numbers 3, 4, and 5. So you play, all of you, you play against me. So if you lose, you buy me a beer. Okay?
Okay.
Okay, so do you want to move first or second? First, go ahead. Your turn.
But we always lose if we play optimal.
Against me, yes, you will.
Well, then let's just not play.
Well, I gave you a choice if you want to be the first player or the second player, which means that you can actually win if you choose the correct player. However, you need to know the... Yeah. Okay. So, your turn.
4 from the third part.
So, instead of 5, you put what?
1.
Okay, so it's 1. Okay, so my turn. And I play like 2.
Faccio la seconda prendo. Vabbè.
Yes, check.
Dove sono?
Dai, raga, un bornivo.
We remove 1 from the first part.
So you put 2 here.
Yes.
Yeah.
2. Then I play 0.
Oh.
Точно
We surrender.
Okay. So do you want to play more? No?
The goal is the same goal. Make it like source. There should be no. Should be zero.
Well, you tell me.
That's a zero strategy.
Really? Okay, so do you want to play first or? I start first. Okay. So let's have 1.
Ma niente, se parte di entrare posso poi.
Da.
Raga, posso fare.
Well, was always the first there. No.
Преди малко загубихме
Ама да, we didn't play optimal.
Ма ти ми играл оптимално.
Ай, ще правим сора на 0.
Ама гър бяхме.
Да,
Ма ние това правихме.
не правихме рандъм.
Трябва да спечелим.
Ами трябва да сме първи част.
Така,
You win again.
Okay. So I have 2 beers now.
Okay, let's play again. We're first.
Okay.
Обмислете добре следващия.
First foul.
2.
We take 2.
Okay.
Хитро, как се сети на това? Шахмат.
No, stand by. The second foul.
Let's take 3 from the second part.
Не, ако махнеш от втората, губим със сигурност. Сега махнеш една от двете крайни.
Да.
Ако махнеш от втората, той ще махне втората, ние ще махнем едната от крайните и той ще вземе последното.
Ама то, който вземе
последното губя.
Take
3 from the second.
Yes.
Ага, загуби.
Yeah. So now you win the game.
Ай сега пълно.
So you owe me just 1 beer now. Okay, so as you might guess, the strategy is almost the same. But if you keep the XOR sum equal to 0, at some point your opponent will leave you with just 1 pile which is greater than 1. So you will have like 1, 1, 1, 1, 1, and some A, yes? Then, according to the normal game, you have to replace A with either 1 or 0. It depends on the parity here, yes? So, and you make just a different move. So why should this happen? Because you always have XOR sum equal to 0. This means that if we have these 3 numbers, A, B, and C, if we write down binary representation, yeah, so that's, let's say, 3, 4, and 5. So we have 0, 1, 1, 1, 0, 0, and 1, 0, 1, yes? So that's the least significant bit, yes? So if the XOR sum is 0, then at each position you have even number of ones. Before your opponent move, he should have at least 2 numbers which are greater than 1. So he cannot remove all of them. And eventually, at some point, he will leave just 1 number greater than 1 for you. And then you decide what to do. So like in this, when you had 3, 4, and 5, we made 1 and 1 here. So according to the normal game, you should have taken all the stones from this pile. But instead of doing this, you just put 1 here. Yes? And if instead of this 1, I put 0 here, then according to the normal game, you should put 1 here. But instead of this, you put 0, and you win the game. So that's pretty simple. So now you know how to play Miser Nim. And now let's learn how to play Moore's game. Which is advanced Nim game. So the rules are the same. So you have like you have some number of piles. But now when you make a move, you select up to k piles, and you remove some number of stones, but at least 1 from all of them.
For all of them, the same number of stones?
No. For each pile, you remove as many stones as you want, but you have to remove at least 1. Overall. No, not from each, overall. So basically, you select any k piles, up to k piles, and you remove as many stones as you want from these piles. If k is equal to 2, then what you can do from this state, you can move to 1, 4, 5, yes? Or you can move to 0, 4, 0. Yes? Or any other similar moves. Who knows how to play Moore's game? Okay, who knows how to find the winning strategy in the Moore's game? Any ideas like X hash or something? Well, so the idea is basically the same. If you write down binary representation, 3, 4, and 5, 0, 1, 1. So in a regular Nim game, when k is equal to 1, you have to make the number of ones in each column to be even. If k is 2, you have to make this number to be divisible by 3. In the general case, you have to make this number to be divisible by k plus 1, and that's it. The proof is pretty similar to the proof of the Nim theorem. So that is a home task for you guys. So now you know how to play Moore game. However, to find the optimal move for the first player is not that easy as in a regular Nim game. But still, it's possible. You have just to select k piles, and you can always do that. You can always, well, if the limits are not high, then you can do brute force. Another interesting game is staircase Nim. So you know this game?
Yes.
You know this game. So rules are the following. You have n piles with stones. So when you make a move, you take some number of stones and you move them from a pile to the left, from the third pile to the second pile, and from the very first pile you just remove them. And so guys, tell me, what is the optimal strategy for the staircase Nim?
Well, should we tell it or?
Yes, you can tell it.
We just ignore the even positions.
Yes. So if we ignore all the even positions, then for odd positions we have to look at the XOR sum, and if it's 0, then it's a p position. If it's non-zero, then it's n position. Okay, why should this work? Let's see. There is a very simple game played on a one-dimensional stripe, and you have two checkers. Okay, white and black, and they alternate. So which actually means that there is black and then white, then black, then white, and so on. So there are n black and n white checkers. So when you make the move, you take your checker and you move it some number of cells to the left or to the right, it doesn't matter, but you cannot jump over other checkers. If you cannot make a move, you lose. So in this particular case, white starts. So who wins the game? White or black? Why?
Because the blacks can block the white one, and they can't move.
Can you repeat the problem statement?
Okay, problem statement. We have a stripe, one by some number, let's say m, filled, and we know the positions of n black and n white checkers.
Isn't it like Nim between the alternating cells?
Exactly. They alternate from the left to the right. First you encounter black checkers, then white, then black, then white, and so on. So when you have to make a move, you take any of your checkers and you move them to any number of cells to the left or to the right, but you have to move at least one cell. You cannot jump over other checkers. Well, since they alternate, the checker to the left and checker to the right will be of the different color, or you will find the edge of the board. So if you cannot make the move, you lose. So that's the Nim game on the number of free cells between the checkers. Well, and here, if the black, so we have 1-1 now, yes, 1-1 position, and that's why it's p position, because it's 1-1. So if white checker moves here, yes, so it becomes 1-2. And in the regular Nim game, it's illegal to increase the number of stones. However, you can just simply move your checker the same number of cells and force your opponent to reach the edge of the board. and you return to 1, 1. And since the board is limited, the game will eventually end. However, potentially there are cycles in a game graph. So the same idea is here. If you take some number of stones from a pile that we ignore, and if we take, let's say, 4 stones, we move them from this pile to the third pile, we can simply forward this 4 stones to the second pile, and they were ignored and they will be ignored after your move as well. So you will simply return to the same position, and since sooner or later they will be removed from the game at all, this game eventually ends. Okay. So also we mentioned this Moore game, and there is also Miser Moore game, which is played the same way as Miser Nim game. You can guess how. Okay, so Nim game is very important in game theory. Why? Because it has a direct relation to Sprague-Grundy numbers. Yeah. What is Sprague-Grundy numbers? Who has heard of Sprague-Grundy? Yes. So what Sprague-Grundy numbers actually are? Instead of this n position and p position, we can assign Sprague-Grundy numbers to game states. And if you have some state S, you have some moves, some edges going out of this state. So Sprague-Grundy value for your state will be what? Minimum excludant, which from the set of Sprague-Grundy values from T, where there is an edge from S to T in the set of edges. Yes? So what is minimal excludant? Yes, it is minimal, non-negative, it's very important, integer, not included in the set. So we have a set of numbers, and we pick the minimal non-negative integer number, which is not included in the set. So for a Nim game, for a one-pile Nim game, what is the Sprague-Grundy value for one-pile Nim game?
N.
It's actually n. Why? Because from 1 stone we can move to 0 stones, yes? And from n stones we can move to any number of stones. So like all the numbers from 0 to n minus 1 are in the set. So that's why Sprague-Grundy value for one pile is actually the number of stones in the pile. For a 2-pile Nim game, what is the Sprague-Grundy value?
Well, the XOR.
Yes, the XOR sum of these two numbers. And for like multiple piles Nim game, it's the XOR sum of all of those numbers. So, and when we are assigning labels in the games, instead of just n or p labels, we can calculate this Sprague-Grundy values, which are actually minimal excludants for some sets. We can calculate them, and when we have these values, there is much more we can grab from the theory. Now we can play multiple independent games at the same time. Like in the Nim game, if we have many piles, we can treat them as a separate games. So if there are 3 piles, you can consider them as 3 independent games. And every time you want to make a move, you choose the game first, then you make a move in this game, and that's it. And if you cannot make a move, you lose the overall tournament. So the same approach can be applied to a general case. You can play different nature games, like chess, okay, then some cards game and some Nim game. You can play 3 games with your opponent, and every time you have to make a move, you choose what game you pick, and then you make a move in this game. And then your component goes. So, and you have to decide who wins the overall tournament. And that can be done using this Sprague-Grundy values. You have just to calculate the XOR sum of the values. In the general case, if you have many games, and if you have already calculated Sprague-Grundy values for all of these n games, then the Sprague-Grundy value for a combination of these games is actually XOR sum of Sprague-Grundy values of the small games. So, and at the end of the day, if you get 0 as the Sprague-Grundy value, it means that it's a p position. If it's a non-zero, then it's n position. Let's consider an example. So you have a stripe which consists of n cells. And every time you make a move, you pick 2 connected cells and you remove them. What? Well, so your goal is just to select 2 neighboring cells and remove them from the game.
The other 2 parts, do they connect?
They do not. So you will, instead of, if you cut somewhere in the middle, then instead of 1 long stripe, you will have 2 smaller stripes. If you remove them from the end of the stripe, that's okay. You will have just 1. So in the middle of the game, you have many stripes. You select any of them, and then you select 2 cells, and you remove them. And maybe you will have 1 more stripe on the table. So what is the winning strategy for this game? How to calculate the outcome of the game? Yes, any ideas? Yes?
Well, we will calculate the numbers for any length of
Yes.
the sequence. And when we want to calculate for length n, for example,
Yes.
we will see all possible cuts and take their XOR, all possible games.
Yes. Basically, let's have this Sprague-Grundy values for all numbers. So we know that for base cases, the value is 0, yes? When we have just 1 or we don't have cells at all. So how to find the value for some number n? So if you want to calculate the nth element of this array, given that you have already calculated all smaller values for smaller numbers, then what you do, you just iterate all possible positions where you put your move. Okay, so that will be the end. Then you will split your stripe into two smaller stripes of sizes. So left size is equal to I minus 1, yes, and the right size is equal to n minus 1 minus I, yes. So we just made a move, and now we have two different, like two splitted games. And we want to know the Sprague-Grundy value for the combination of these two independent games. So we have just to take the XOR sum. So we will have some value which is equal to Sprague-Grundy at position left, XOR Sprague-Grundy value at position right. Yes? And for all those we have to, okay, let's have some set, yes, of integers and let's insert v into the set. So eventually the value we should put into this position is minimal excludant of used. Yes? Okay, so that's the way how we can combine games, or how we can add games. And this operation is called Nim sum, because we add some Nim values. And some game state, it does not depend on the game. If it has some Sprague-Grundy value equal, let's say, to x, then we say that this game state is equivalent to one Nim pile with x stones. Because important properties are the same for Nim pile and the game we are playing now. However, that's the one way how we can combine the games. We can also multiply games. There is the game which is called two-dimensional Nim. Have you heard of two-dimensional Nim game? No. So let me show you how to how to play two-dimensional Nim. It's much more interesting than one-dimensional. Okay, so imagine that you have a 1 by infinity long stripe, and there are cells, there are indices, and so on. You have coins at some positions. You may have more than one coin at a position. So at each turn, you have to move one coin from the right to the left. And you can put it anywhere you want.
Exactly one. Exactly one?
Exactly one coin. Exactly one coin. And you have to move it at least one cell to the left. So what is this game? That's just an Nim game. Just an Nim game, because that's like the length of the pile. You just shrink it. So that's the Nim game. So what we do now, instead of this one, we extend it to two-dimensional. And now it's like a infinite quarter plane, yes? And you have these coins anywhere you want. And every time you take a coin, you move it like anywhere in this direction, anywhere, but at least one cell. So you can move it here, or you can put it here, or here, or here. And that's much more interesting. Okay, well, in fact, you cannot do this. You cannot do this. You have to, when you have a coin, you should put it wherever you want here. And that's the way how we can multiply games. And there is another operation. Along with the Nim sum, there is a Nim multiplication, which is not that straightforward as Nim addition, because that's just XOR sum. This is somewhat more complex, but still, you just have to be aware of such a thing as a Nim multiplication. And Nim multiplication allows you to multiply the games, and when you multiply the games, the rules are a bit different. Imagine you have two games, two separate games, and you have to make two moves simultaneously in both games. Like here, when you move some coin, it means that in this projection you will do something, and in this projection you will do something. So this is a kind of like two separate Nim games, and you make moves in both of them together. Okay, and I believe that's it for today. Do you have any questions?
How to solve this problem?
Yes, that's so.
How to solve this problem? You have to calculate Sprague-Grundy value.
Well, yes, but
for, you have two separate games. So you project all the coins to x-axis and then to y-axis. You have two separate Nim games. You calculate Sprague-Grundy value, which is a regular XOR sum, and then you have to calculate Nim. You have to multiply in terms of the Nim these two games, and there are some not that, but kind of complex rules how to do that. Well, first of all, you have Fermat numbers, like Fermat powers of 2 in this kind of shape. For those numbers, A multiplied by B, where B is less than A, is equal to just A by B. And if you have Fermat power of 2, and if you multiply it by itself, it is equal to this number. And also the third point is that Nim multiplication and Nim addition, they form a mathematical field. So there is 0 and there is 1. So all rules, they are hold there. So distributive and associative rules, they are hold there. So you can, if you have some number, let's say 17, and you want to multiply it by 16, then it's actually equal to 17 plus 1 multiplied by 16. Yes, which is equal to 16 by 16 plus 1 by 16. So this is equal to 2 by 16 and plus this is just a regular product, so that's 16. And this is 24. So you have 24 plus 16, this is 8. So something like this.
Easy. Easy one.
How is 17 equal to 17? So
Oh, no, that should be 16. But that's not a regular addition, that's a Nim addition. That's like XOR addition. Okay. Yeah, so these are just hints for you. You can easily Google it and you can find much more information on this topic. So that was pretty short lecture. It's the goal of the lecture is not to teach you everything what is related to the game theory. It's just one of the showcases. There are a lot of topics, and like the main message is to set a goal and work hard, and then eventually you'll find yourself at the level that is good enough to just achieve your goal. So I wish you good luck, and if you have any questions now or later, don't hesitate to email me. Okay, so thank you very much for attending.